Okay, cool. So yeah, so we're gonna talk, it's mod 2, beginning of mod 2. So section 13, intro to linear algebra. Note that we're gonna go through 3 different little notebooks. I have it up on GitHub, so you guys have that link already. So you guys can follow along. Just know that most of this stuff is borrowed from the curriculum. You'll probably see, if you go through the curriculum and see this too, you'll probably see really similarities. A lot of times I'll just copy and paste it. Sometimes I kind of rearrange the code, but I try to keep it, try to follow the curriculum the best you can, so that way you're familiar with it, right? So linear algebra. So first things first, like why do we need linear algebra? Well, kind of going a little meta is that we need linear algebra to do a lot of the rest of the course. And like basically just know that a lot of data science and really computer science is built on top of linear algebra. So, and the reason why I do linear algebra, we'll see a little bit why, but basically it's a bunch of vector spaces. So relationship of linear relationships. So linear algebra, linear relationships, lines, it all comes together. The difference is linear algebra in general doesn't have to be just 2-dimensional or 3-dimensional. It can be as many dimensional as you want. And so that's actually one of the reasons why it ends up being so useful in both data science, but also computer science, is that basically you can think of your data as multidimensional. And you can think of like essentially like each column as a new feature, as a new axis of this dimension. So we call these vector spaces basically like, think of like you back in like, grade school, we talked about like the coordinate plane, X and Y, and X, Y, Z. Those are kind of like our vector spaces. Essentially, there's whole definitions I could talk about mathematically, but we're not going to go into that. But the main things you have to know is that there's spaces spanned by vectors, and we'll talk about what those vectors are. But basically, it's just a bunch of lines in there. Okay, so we'll use things called vectors. We kind of talked about this before. Matrices, you guys are probably familiar there, and something called tensors, which is becoming more and more popular of a term, which is funny. I remember back in like physics, we talked about tensors all the time, like for certain mathematical stuff, and no one talked about tensors. It was kind of like, oh, matrices, vectors, and that's kind of it. Maybe some fringe stuff had tensors. Now you'll probably know machine learning, for example, one of the more popular packages called TensorFlow, open source from Google, built on tensors. So tensors are going to come up now. And the main thing you have to realize, if you know what a matrix is, a tensor basically is a general matrix. That's kind of what a tensor really is, okay? So there's a few other things we can do with linear algebra. For example, we can do mapping, which basically takes a feature and projects it onto another part of the dimension, and then we can do some stuff. Did I see a hand raise?
I have a question, yeah.
Yeah, go ahead. Yeah.
Is tensor kind of like identity matrix, or is it something different?
An identity matrix, well, that's not the best way. A tensor, identity matrix is a tensor. Not all tensors are identity matrices. And so we'll see, like we'll see this kind of general idea, and I think we'll see in a bit.
I took linear algebra, but I don't remember them saying anything about tensors for some reason.
Yeah, exactly, because no one uses the word tensors. That's why I thought it was hilarious when I mean, for example, give you guys some idea. You guys know general relativity, like the idea of general relativity for Einstein, stuff like that. In physics, it's you sometimes see it like if you're watching some like Discovery Channel and it shows like the little equation for like Einstein's equation, and it's like it's really simple equation. It's very small. Of course, you don't know what the symbols are, but it's really small. It's like, well, yeah, I guess it's simple, but it's like it's a 4D tensor, and so it actually turns out to be 16 equations in one. So that's just like the things that we would like say, like, oh, the tensors and tensor algebra and stuff like that. But basically, it's just a generalized matrix for higher dimensions, and we'll see what that looks like in a second. But yeah, again, if you were in school, maybe like, I'd say like 8 years ago, there's a pretty high chance, unless you were in the fringe part of like science and math, you probably never heard the word tensors. I talked to other math majors in college, and I'd say tensor, and people are like, what? Like, it's not a thing. Now it's super common. So I just think it's funny. Anyway, good question though, Kevin. We'll get into it. But dimensionality, basically dimensions, something called PCA, which we'll talk about much further in the future. But that's, if you guys remember multicollinearity from like your project that you just did, we can do dimensionality reduction with basically doing projections and stuff with linear algebra. And basically almost every ML application, not every, but most machine learning applications has some form start off in linear algebra, okay? So something to kind of think about. And then we'll also do things from very abstract ideas and put into a formalism of linear algebra. So for example, like pictures, we can actually take pictures, which are like a bunch of pixels, and we can actually create like a vector or a matrix of these pixels. Or for example, language, natural language processing, we can actually create vectors out of words in sentences and basically make these, use the formalism of linear algebra, kind of like the linear algebra superpower, and be able to apply it to things that seem a little more not as, mathematically, not traditionally mathematically associated, if that makes sense. And again, I'm talking very vaguely here, but trust me that we'll use linear algebra pretty much all throughout the whole thing. Okay. So now we're going to talk about some definitions and stuff like this. So this is kind of like what Kevin started hinting at, like what's a tensor exactly. So the first thing you probably recognize is a scalar. Again, it depends, what your background is in mathematics, but scalar usually is referred to just essentially as a number. You can think of it as like a 0th dimension. There's just like one part, so you can think of it like a point. Okay. We also have vectors, and vectors are considered, like basically like maybe a list of numbers. Here, there's only 2 numbers, but it can be like 1, 2, 3, 4, 5. You can think of like one-dimensional, basically like a line of numbers. Then we have something, a matrix, okay? And a matrix, 2-dimensional, so you can think of like a plane, for example, like a flat sheet of paper. And then again, now that tensors are becoming much more common, it used to be called like 3D matrices. So for example, you might see some older literature talk about 3D matrices. Usually now we just call them tensors. Just because tensors can also be 4th dimensional. So you can think of it like, if you can kind of like go back and like, I'm going to start really small and then go back up. If we start off with a scalar, a vector is a bunch of scalars, a matrix is a bunch of vectors, and a tensor is a bunch of matrices. And then if you go higher up tensor, it's like, oh, if you have like a 4th rank tensor, it's a bunch of 3D matrices or 3rd rank tensors. And you can go higher and higher up to like however dimensions you want. So again, basically every data column you can think of is a new dimension. So we can have something like if you had 20, dimension or 20 columns, 20 dimensional, you'd have a 20th rank tensor. Okay. So again, tensor just we stop naming them after a certain point. Okay, cool. All right. So now we can actually create these with NumPy. Oh, should probably run this first. Okay. So we can actually create these different entities, like these different objects with NumPy. So the first obvious one is a scalar, which is a number, but we can actually make it with NumPy. So you'll notice here, right, I think we might have seen this, maybe not, but I'm calling the NumPy package and then just a range. So you might notice like range for before and it created like a range of things. I can actually call like a range and it'll create basically these different entities. So if I call it with just one number, it just creates basically just a little range, just one little number here. In this case, it's just an array. Okay, and note these are NumPy arrays. Okay, so that's kind of simple, not really exciting. But for example, if I wanted like 4 numbers here, for example, I can actually say v is equal to np range, and I can display this vector right here. So note that this is basically like a list, but it's wrapped around a special thing called a NumPy array. So note that this special thing. And also note that if I do print, it'll print out just a list like this, but it's not actually, if I do a print type, you'll see that it's not in a list, it's actually a NumPy array. And there's actually a little subtle, if I do print v versus print, 1, 2, 3, you'll see that NumPy arrays will not have that comma in there, and then list will. Usually though, you'll see me do display because that is usually what we see when we have the last part in there. If I don't put display, if I just put it like this, it's calling display. So just kind of know. But anyway, just know that it's basically a list of numbers now, and it's wrapped around this special thing with a NumPy array. Okay, and so that's one we can define and arrange. So you can see like 0, 1, 2, 3, going to 4. If I wanted to go up to 10, you can see go up higher. There's other ways you can define a vector. This is super useful called, well, this is like len space, but like linear space. And basically you have a start. In this case, it's -pi, 2 pi, and then separated by 10. So there will be 10 elements. So I can actually create a vector now here, going from -pi, -3.14, and then it'll figure out the spacing for me, and it'll do 10 times up until pi right here. So for example, to make it a little simple, if I did something like -10 to 10, you can see it splits up like this.
It's kind of like MATLAB. Like MATLAB has something like that.
That's exactly right. Yeah, if you're experienced with MATLAB, it would have very NumPy and MATLAB will have some very similar attributes. In fact, I don't think I talked about it, but I think the curriculum does. Is that you can use the printout of MATLAB like vectors and matrices in NumPy. You can actually call it up directly. So if you're familiar with that, it's super useful.
Yeah.
Okay, cool. All right. So anyway, linear space, useful. You'll see that a lot. Okay. So the next thing after we have a scalar, or after a scalar, we have vector, and then we have a matrix. And so here we have, so you'll note right here, if I just put in this part right here, this will just be 8, 4 times 2. Okay, but if I do a NumPy arrange, right, you can see like, okay, it's just a vector, but I want that into a matrix. Remember, a matrix is kind of like an array of, it's like a bunch of vectors. So I can do this dot reshape. And what this will do is saying, hey, change it to the shape of 4 rows, 2 columns, right? And you can see here, it will be 4 rows, 2 columns. Note that I did it this way just because it makes it easier just to quickly like see how these things are going to be arranged. I could have just as easily put like 8 here. And you can see, obviously, that works the same. But if I try putting like 3 here, note what will happen. It'll give me an error. It's like, hey, whoa, you can't do that. It's not the right size. And says like, oh, if I have like 6, then that would be fine. Okay, so note that this reshape has to have the right, right number of elements in here. Okay, so that's why I'll usually write it like this, just to make it easy for it to read through. Oops, forgot my other number. Okay, cool. And you can see here, like I like to think of it, it's like a matrix is a list of vectors. You can see here's my first vector here, my second vector here, my third vector here, my fourth vector here. Okay, so that's kind of like how you can kind of picture a matrix. Okay. Question?
Is a matrix always an even number of vectors?
Oh no, I could have done like this. It's just whatever you want. Yeah. We'll talk about things like identity matrices and invertible matrices, and those ones you turn out have to not just be even but also square, which means like you have to have like for example like a 3 by 3 or a 5 by 5 or a 4 by 4. This matrix would not be invertible. Basically, it wouldn't have an inverse. We'll talk about that. Do math with tensors. Okay. But yeah, you can do whatever shape you want, however many vectors, however big the vector is. I could have been like 15 here, and it would have been just as fine. Okay. Cool. All right. So this brings us to our tensor, in this case, a 3D tensor. And so we went from a scalar, which is kind of like a 0th dimension, to a vector, 1 dimension, to our matrix, which is 2D, and now we have a 3D tensor, right? Just know that you could technically call all of these things tensors. We traditionally don't, just because it makes more sense. It's kind of like when we do like the square root, you know, and the cube root, but we don't really have like a 4th root name. We just call it the 4th root, the 5th root, the 6th root, and so on. Kind of the same idea here. We just use these so often that we just call it a specific name. Okay, and history also, we've had specific names for it. But now we have a 3D tensor. So I can do the same thing, NP arrange. In this case, you can kind of see my breakdown. I have 4, 2, 3, and I'm reshaping it into 4, 2, 3. And so when we see this now, basically, you can think of a tensor as basically a list of matrices, or you can think 2D tensors. So you can see here, this is my first matrix, my second matrix, my third matrix, and my fourth matrix. Okay, so you can kind of think of this like, oh, how many matrices do I have? Inside each of those matrices, how many vectors do they have? See, each one has 2 vectors. And in each of those vectors, they each have 3 elements. 1, 2, 3. Okay, 1, 2, 3. Make sense? Okay. Yeah, any questions? Thumbs up, thumbs down, sideways? Cool, all right, awesome. So good. So, and just know we can expand further. If I wanted to do like 5 dimensions, for example, or sorry, 5 dimensions, let's say 4 dimensions, I could have done something like this. And now basically each one of these elements, this first element is a 3D tensor. So you can imagine how quickly we can go like really, really far into this. And note that too, the number of elements, it's just the number that's multiplied together, right? Or in this case, the shape. So for example, 5 times 4 times 2 times 3 is 20, 40, 120. So it should be 120, and there you go, 120 elements. So that's how we can quickly figure out how many is in each part. Okay, cool. So now we have our different parts, our matrix, our tensor, our vectors. We can actually start slicing them. So the vector is probably the easiest one. So remember, our vector just looks kind of like a list, right? And so you'll probably feel the most familiar with slicing with, or actually indexing, but basically going through the vector. So for example, this one right here, this display from V1 to 4 will give me the first 4, or starts from the 1th element, obviously skipping 0, only to the 4th. So you can see here, it gives me 0, 1, 2, 3, just like you would do with a list. Right here, hopefully we've seen this before now, is that this basically will get every other element. Basically it's saying, oh, go from the beginning to the end, but then count by 2s. So we go from 0 to 4, 6, 8. Okay. Here we're just getting the full vector, basically the beginning to the end. Okay. And then this fun trick, we can reverse the vector, basically going from the beginning to the end, but go backwards, count with -1. Okay. Any questions on this? Okay. Cool. Yeah. So again, this is just like a list, right? It's pretty much the same operations you would do with lists. But now we start getting into more interesting things like a matrix. So, and one thing you'll start seeing now is like, hey, this is really similar to like when we do pandas with like dot lock or doc ilock. We can actually start seeing like what is familiarity, and that's because pandas is actually built on top of NumPy arrays. So this is why we can do these kind of things. So you can see here, this one's going to give me, and I'm going to split this up. So this is my matrix, right? Oh, I made my matrix really big. Oh, that's right. We'll make it smaller so it's easier to see, right? Okay, so you can see 5, 3. So there we go. All right, so I'm going to go ahead and split this up so I can see this a little bit better. But you can see here, this is going to be the first element, or sorry, the first row, the first column. The way I like to think about this is kind of like saying it's the first vector and the first element in that vector. So in this case, we'll see number 0. Okay. If I wanted the second vector, right, first element, this would return us what number? So first vector, yeah, I saw 3 there. Good. So 3, and you can see 3 there. Okay. So you can kind of see like, okay, if you think of it like what vector is taken, you can think row, column, but when it gets really big, it starts getting confusing. Like what's a row, column, depth, you know, 4th-dimensional height? I don't know. So something to consider. So you can start out seeing like, okay, this will give us the last vector, the last element. So that would be 14 here. Okay, and I'll just let this run through. So you can see 14's here. I can get basically the 0th, the very first vector, and then return all the columns. So you can see that's the very first vector with all the columns, basically all the elements in there. We can get all the vectors, but just get the first element of each of those vectors. You can see it's going to be 0, 3, 6, 9, 12. And you can see that's what pops up right here. And then we can also, of course, just get all of the full matrix itself, which in this case, you get the full matrix right here. Okay, cool. Any questions on this so far? Okay. Can you guys see this okay? It's not too small, is it? No? Okay. Cool. So, okay. So this goes to the tensor part. So this is where I like kind of like use that analogy of saying, oh, it's the first vector, the second element. This is where it helps really a lot with tensors. So remember our tensor is pretty big here, right? It's 24 different elements. So we can think of like getting the very first, like the 0th element of the tensor as being like getting the first matrix, this guy right here. Okay, so you can see this is we'll see 0, 1, 2, 3, 4, 5. If I put, for example, 2, this will give us the third tensor, 12, 13, 14, 15, 16, 17. Okay. Next part we have right here, we have our first, or we have 0, 0. So this is giving us the 0th, like the 0th matrix, the 0th vector. So that should be 1, 2. So we go to run that. You can see 1, 2. Not too bad, right? Okay. So then here we can see something similar. It's like, okay, we have 0, 0, 0. So the first matrix is the first matrix, the first vector, and then the first element of that vector. So we should get what number in this case? You can just write like 0, 1, 2, 3. 0, good. Kind of hard to see up there. Hopefully you guys can see that. Okay. So yeah, you can see we get the very first vector, first matrix, the first vector, and then the first element. If I change this to, let's say 2, okay? So remember, what number would this be? Number 2, good. Yeah, it's kind of easy in this case, right? So 0, 1, 2. So remember, I'm getting the first matrix, the first vector, and then the second, coming from 0 element, which in this case is just 2. Okay. And so you can kind of see here is kind of similar. We get the first matrix, which is that guy, the first vector, and then just get all the elements, right? In that case, we should get 0, 1, 2. Okay. And so this one's a little trickier to kind of think through, but just I'd say break it down. So you get the 0th. So again, looking at this guy right here, we're getting the first matrix, and then we're getting all of the vectors, right? But then we're only getting the first element, so 0 and 3. So we can see here, we now have a vector of 0 and 3. Okay. And so this one's, again, a little trickier. Same idea. We have the first matrix, all the vectors, but then we're getting from the first to the end elements. So we're getting 1, 2, 4, 5. And you can think of it as like, well, okay, we're getting those parts, so this should actually be a matrix. And you can see we get 1, 2, 4, 5. Okay, cool. How are we feeling on that? Thumbs up? Sideways? Pretty good? Okay, cool. Yeah. So again, I like to say, like, I would say the best thing to do, this is how I think of it, you guys can tell me, but I think of it like when you're slicing through, you're getting the first matrix, the first vector of that matrix, and then like the first element of that vector. So that's how you can kind of slice it through, right? So again, that's slicing. You'll see this quite a lot when we're going through a lot of different mathematics. So some basic properties, something called shape. So I kind of alluded to this a little bit, but this helps us kind of figure out what the size of some things are. So for example, if I, again, just define a scalar, right? I can print out that scalar, and I can also print out something called its shape and its size. So these belong to the actual S scalar here. So I can see here, I have my scalar, which is just 100, right? I should really put display just to make it clear. Because it's not just a number, you can see there's an array around here, right? So I have my scalar, which is just one number, and you can see its shape, in this case, is just printed out as nothing. Okay, there is no shape to it. You can think of it like a 0th dimension, and you can see its size, well, there's only one element in it. Okay, so our vector, so I'll show you our vector again. This is our vector. So our shape here, okay, that's going to show us basically like the dimensional size of it, and then the size itself, which is how many elements. So in this case, the size, this should be pretty easy to figure out. It should be 10. The shape's a little trickier, but basically it's a tuple with just 10. It's basically, all it is basically 10 elements in that one dimension, okay? So now we have our matrix here, okay? And remember we have all of these parts. We have 1, 2, 3, 4, 5 rows, right? 4 or 5 vectors, and then each of those vectors have 3 elements. So we have a total of 15, right? So I'll just put this on here just to show you, 15. Okay, but the shape now, it's 5. It's 5 vectors. Each of the vectors have 3 elements. Okay, so let's go to our tensor now. See our tensor now, we have basically 1, 2, 3, 4 matrices. In each of those matrices, there are 2 vectors, and then in each of those vectors are 3 elements. So first of all, size is pretty simple, right? Just the number of elements. In this case, you can just look at it right here. It's 24. Okay, but that last part, the shape, right? It's a little trickier. So we kind of know, like, I think you guys probably can figure out, it's like, okay, the shape's going to look something like some number, comma, some number, comma, some number, right? So let me ask you guys, okay, who wants to tell me what this first number should be based on kind of like what pattern we've seen so far?
4.
Okay, so 4. Okay, and what's that correspond to, Josh? Just to kind of make it clear.
The number of vectors in the tensor.
Good. I think you meant matrices, right? Or
Yeah, matrices.
you got it, yeah. So number of matrices that are in that tensor. So good. So what's the second number? Someone else give me what that number should be.
Is it going to be 2 or?
Okay, so 2. All right. So what are you thinking? Is why would it be 2? I'm not saying you're wrong or anything.
It's two vectors per matrix.
Right. Yeah. So each matrix, we already got how many matrices we have, and in each matrix we have 2 vectors.
Mm-hmm.
And then Griffin, do you want to help us out with that last one? What would be this last number?
3.
3, right? And what would that 3 correspond to?
3. elements in the blanking
It's a lot of words, right?
the vector.
Yeah, in this vector, right? So each of these vectors each have 3 elements. Each of these matrices have 2 vectors, and this whole tensor has a total of 4 matrices. So we can see we have 4, 2, 3. You guys got it. See, it's not too bad, right? You just kind of have to break it down a little bit. And I think that's why also I like doing the display better. So you can kind of see this a little easy. I think it looks a little easier because the commas are there, but each their own, right? So you can kind of see it's like, okay, they're kind of grouped together in that certain way. All right. So any questions on shape, size, anything like that? Yeah. Pretty good. Cool. So we'll move on to the last part in this section is our transpose. So transpose, again, depending on like your familiarity with mathematics, you might have heard this before, you might not. Transpose basically, I like to think of it like you're turning it on its side. That's not exactly it, but a vector is probably the easiest one. So our vectors, you notice, are all like, horizontally printed out. We can actually have it so our vectors are this direction. And the reason why we'll do transposes are basically to allow us to do multiplication. So we'll find when you're linear algebra, you get to have certain shapes. And for example, if you want to multiply a matrix by times the matrix, sometimes you do a transpose to make sure that matrix math or that tensor math works out properly. So just to kind of show you guys, we have our first, oops, give you the answer. We can see our first matrix, right, M, right? We can see it's a 5 by 3, right? So it means 5 vectors, okay, of 3 elements each. And now we just call dot T to do a transpose. You can also do something else, but I usually do dot T just because it makes more sense. But you can basically, oh, here it is, transpose, right? You could do NP transpose. This is just so much quicker. Usually I do dot T anyway, okay? But you can see here is that if we do a transpose, we now have 3, 5, which means 3 vectors of 5 elements each. And you'll see here is that basically you can see that first vector is essentially these columns, 0, 3, 6, 9, 12. 0, 3, 6, 9, 12. And same thing over here. So you can essentially think of it kind of essentially turn on its side. We're basically transposing it where we're now able to keep those separate. So now the last one, okay, so the tensor. So this one's a little tricky in my mind, okay? But you can kind of think it's like, okay, we're gonna reverse it. So the shape should be the opposite, which will be 3, 2, 4. So we saw originally was 4, 2, 3, and then it goes 3, 2, 4. So we'll have, instead of 4 matrices with 2 vectors, each with 3 elements, we'll have 3 matrices with 2 vectors each of 4 elements. And you can see here, that's exactly what we have. We have 3 tensors, or 3 matrices like this. And each of those matrices, we have 2 vectors, like we had before, and then each of those have 4 elements. So you can see here, this one's a little harder to see, in my opinion. Maybe you guys can see it better than I can. But basically, you can think of it like you are, how to say this? You're taking the transpose within it. So you can kind of see is that this is kind of like its matrix. I'm not even going to go into it. That's going to confuse you more. Just know that this is our transpose. There's a lot more resources to talk about transpose. If you want to know, you can think of it like, I don't want to give you guys the wrong thing. So I'm debating about if I should say this. But you can think of like, remember how I said the matrix? So you can think of this matrix right here. This matrix that we had originally, this up here. Oops, I can't scroll. There we go. Okay, so we have this original matrix. You can think of this matrix. Let me see if I can get this drawing out right. We can think of this matrix right here as essentially like vector 0, vector 1, vector 2, and so on, right? When we do a transpose, it's like we're now taking the transpose of those parts. So we have now this whole vector transposed over, okay? So you can kind of think of it, maybe it's not the best way to think of it, but you can now think of it like, okay, now we have V0, V1, V2. So you can kind of see like there's now V0 and V0 right here, okay? V1 was right here, V1 is right here. You can kind of think something similar with here. The problem is you have to transpose the matrices. So if you think of like our matrix as saying, okay, in our tensor, we have like M0, M1, and so on. Okay, you can keep going. You can think of like the next part essentially saying, okay, we're taking that matrix 0, M1. The problem is now it's like, okay, we can't just simply think of it like that. We also have to essentially do a transpose of these as well. Okay, so again, I'm not going to go into detail. I'm not going to dwell on this. If you are curious, there's literature on that pretty easily where you can find the math of how matrixing tensors. But it's definitely hard for you to see, or at least it's hard for me to see as you get deeper and deeper into more dimensions. But know that you can do a transpose for any general tensor. Okay, any questions that we've got so far? Okay, cool. So next part we'll do math tensors.